Okay, so actually I'm recording it for the second time because first time for some reasons it failed to be recorded, and I'm just going to share my screen. Okay, so since it's the second recording, I already have the algorithms implemented and some notes made, but and I'm just going to go over what I have written and explain. I think this is the fastest way of doing it. Okay, so yesterday when we were solving this Dijkstra's algorithm, I wasn't quite sure about some places. For example, this edge going back, and the reason for this was that I have read, so as you can see in this, I have read this book, and this book says that Dijkstra can only work with directed acyclic graphs, and that's why seeing that cyclic graph in Dijkstra, I was hesitant. But it turned out that the author of this book made a mistake, and Dijkstra can actually work with cyclic graphs as well. So considering that, this is like the solution was okay, totally, and but I still need to check this solution for correctness from professor. So, but for now, this I assume that this is okay. And for the extra, I want to make some remarks. I just want to highlight that Dijkstra cannot work with negative weights. And here I just showcased an example which explains why. You can pause the video in here and just take a look at the Dijkstra algorithm run in this table and look at the graph and see it for yourself. And the next thing I want to mention is that is here. So in Dijkstra, we always have an invariant, which always has to be true. And this is the following theorem. So it says, when we select vertex U for expansion, then we have already found optimal path to U, provided that d value of U is smaller than infinity. So, and that simply means that once you have your nodes in here, then that means you have already found some short paths to these nodes. Yeah, that's it for Dijkstra. And I want to continue with directed acyclic graphs. I just want to remind you the definition of it. As it says, it's directed and acyclic, which means there is no loop available from the source. And also the single source shortest path problem has solution when it doesn't have any negative cycle inside the graph. And I also want to show what is the definition of negative cycle. So please read this definition. It says a loop of a directed graph is negative if the sum of the weights of its edges is negative. So this is the example. This is a negative loop. And another remark I highlighted here is that undirected graphs are modeled with directed graphs here, and that means that if an undirected graph has a negative edge, it means that it has a negative cycle. So please make sure to kind of I don't know, review these definitions, and we continue with the exercise from the sample, which is this one. Not this one, but yeah, this one. So we have this graph, and we need to run a shortest path single source shortest path algorithm on it. And the source vertex of this graph is going to be S. So as you can see, this graph can have negative weights, and this algorithm can handle negative weights, unlike Dijkstra. And the very first task when you receive such kind of exercise in your intern, you have to make a topological sort. And topological ordering is done in the following way. So given the source vertex, you discover it at time 1, and you just follow its ongoing outgoing edges. So in this case, it's has outgoing edge to t and x. And you have to follow them in an alphabetical order. So you first go to t, you discover it at time 2, and you go to its ongoing edge, outgoing edges, x, y, and z. You follow the order, and so on and so on. And for example, when you reach z, you have no outgoing edges, and you have to finish it here. And once you finish it, you have to put it into the topological order as the last element of it. And you just follow the same logic. You come to y, you have to consider if it has any outgoing edges except this one, but it doesn't have, so you finish it here, you put it here, and so on and so on. Pretty algorithmical problem. So you just have to follow the algorithm, and you put everything in here. You're ready with the sorting, but you might wonder, why don't we have this R in the sorting? And the answer is that it doesn't have, it is not reachable from S. So that's why we don't consider it. Because I just want to remind the problem we are solving. We want to find shortest path from this to every other vertex, but it should be the shortest. So that's why if something is not reachable from S, then we even do not have to consider it. And you just draw your table as the second step of the algorithm. And these are the same, like you have to set them to infinity, nulls, and then you put the very difference from Dijkstra is that when you expand the vertex, you have to follow this topological sorting from left to right. For example, in case of Dijkstra, it was that you choose the source vertex, and then you choose the minimum, the one which has minimum weight. But in case of single source short path algorithm on DAGs, you follow this order. So you expanded it, you reached, you found its children, you set them here, you set them there, and as the second element you choose t, so t is here, and you see that t has x, y, and z. And while calculating the z values, you also need to add the cost of t as well. So for example, this way is 2, and to get to x, you need to travel 9 miles. So this is going to be 9. And 9 is not better than 6, so therefore you ignore the new value and keep the old value. But this is different in case of y, because you say it's 2 and it's 4 and it gives us 6, and 6 is smaller than infinity. That's why you keep it. The same goes for z. It's going to be 2 and 2, 4, so on and so on. You just do the same logic here and same here. Yes, and then as the very last step, you just pick the last element of this topological sorting, and its cost is 3, but z doesn't have anything going out, and here you finish, and the final result has found the shortest path from source to any other vertex in the graph, and these are the corresponding parents of those vertices, and here the algorithm ends. And also I'll make sure to double check this solution with professor and let you know about the results. And in the next video I'm going to do the Bellman-Ford and the Floyd-Warshall, and that's it. I think there was also something I wanted to mention, I guess. No, I have mentioned all of them. Yeah. So this is all for this one.